I am very happy to study the concept of trigonometric function with you today. We know that mathematics comes from reality, exists in reality, and serves reality. There are a large number of cyclical phenomena in the objective world, for example, sunrise and sunset, pendulum movement, etc., and uniform circular motion is the representative of periodic phenomenon in real life. In the previous study, we know that function is an important mathematical model to describe the law of change in the objective world. So what function model should be used to describe the law of motion of uniform circular motion? As shown in the figure, point P is a circle, the circumference is a little longer, and point P starts with a and makes a uniform circular motion. In the above study, we already know that the position change of point P can be characterized by the size of angle alpha, and the size of angle alpha is independent of the radius of the circle. So our task now is to establish a functional model to describe the position change of point P. What tools do we need to study this task? First of all, we need to establish a function model. We need to establish a rectangular coordinate system. Then we cannot study the position change of point P without the unit circle with the help of the concept of arbitrary angle. Therefore, as shown in the figure, a rectangular coordinate system is established with the center O of the unit circle as the coordinate origin and the ray OA as the non-negative half-axis of the x-axis. The coordinate of point A is 10, the coordinate of point P is xy, and point P starts to move on the unit circle from points A, 1, 0. In this way, our question naturally arises. What are the variables in this motion process? Judge whether there is a functional relationship between them. If yes, can you write the analytic expression of the function? Through the analysis of the image, we found that there are 4 variables. They are the abscissa x of point P, the ordinate y of point P, the arc length L, and the center angle alpha. So which 2 of these 4 variables, alpha, can form a functional relationship? First, let's look at the variables xy, because xy are the abscissa and ordinate of point P. We make a vertical line to the x-axis through point P, and the vertical foot is m. In the right triangle POM, we can know that the square of PM plus the square of OM is equal to 1. That is, x plus y equals 1. Therefore, the correspondence between x and y does not conform to the function definition. We have studied the relationship between variables L and alpha in the previous radian value research, so we will not explore it here. Through image analysis, we can further find that the relationship between variables x, y, and alpha, and the relationship between variables xi and L are equivalent. So here we only need to discuss the relationship between the variable x, y, and alpha. To study the variables x, y are actually the coordinates of the study point P. The problem is how to find the coordinates of point P if the terminal edge of angle alpha and the element intersect at point P. The size of angle alpha is uncertain. Our problem is how to study the general problem. In mathematical research, it is a common way for us to do specialized research. So we might as well set alpha as a special angle, 1/3 of pi. At this time, point P is in the first quadrant. We make PM through point P perpendicular to the x-axis at M. Therefore, in the right triangle OMP, we can get that the OM length is 1/2 and the PM length is equal to 3/3. The recombining point P is located in the first quadrant. We can get that x is equal to 1/2 and y is equal to √3 of 2. Therefore, the coordinate of point P is 1/2 and the root of 2/3 is 3. So again, let's take a value. When alpha equals 2/3 of pi, what is the coordinate of point P? We can repeat the steps just now. When alpha equals 2/3 of pi, point P is in the second quadrant. Let's make point P and make P vertical x-axis and M. By analyzing the right triangle POM, we can find that the length of OM is equal to 1/2 and PM is equal to √3 of 2. Since point P is in the second quadrant and x is equal to 1/2 of negative, the coordinates of point P are -1/2 and √3 of 2. Through 2 examples, we find that when alpha is equal to 2/3 of pi and alpha is equal to 2/3 of pi, the coordinates of point P are uniquely determined. Is this result general? Can the coordinates of point P be uniquely determined for any given alpha? Because the radius of the element is constant and the coordinate value of point P is related to the size of angle alpha, when angle alpha is determined, the coordinate of point P must also be uniquely determined. Let's give an angle at will. Let's observe the coordinates of the intersection P between the terminal edge of angle alpha and the unit circle. What will you find? Can we use the language of function to describe this correspondence? For any angle alpha, the abscissa and ordinate xy of the intersection P between its terminal edge and the element are uniquely determined. So there are two corresponding relationships here. The first correspondence, any angle alpha, is expressed in radian system for the abscissa x of point P. The second correspondence is the ordinate y of any angle alpha with respect to point P. For any given alpha, the coordinates of the intersection P of its terminal edge up and the unit circle, whether the abscissa x or the ordinate y, are uniquely determined. So the abscissa x and ordinate y of point P are all called functions of alpha. We define these functions. As shown in the figure, the angle alpha is an arbitrary angle. Its final edge up intersects the unit circle at points P, x, y. At this time, we call the ordinate y of point P the sine function of alpha, and record it as sine alpha, that is, y is equal to sine alpha. Call the abscissa x of point P the cosine function of alpha. Remember cosine alpha, x equals cosine alpha. The ratio y to x of the ordinate and abscissa of point P is called the tangent function of alpha, and is recorded as tangent alpha, that is, the outer ratio x is equal to tangent alpha, and x is not equal to 0. What is the corresponding relationship between sine function, cosine function, and tangent function? When the angle is below radians, we regard it as real alpha. At this time, it corresponds to the ordinate of point P. This correspondence is actually the correspondence of sine function. Similarly, the exponential alpha corresponds to the abscissa x of point P, which is the correspondence of cosine function. What about tangent function? We find that when the abscissa of point P is 0, the terminal edge of angle alpha is on the y-axis. Alpha is equal to pi of 2 plus p, and k belongs to z. Therefore, under the condition that alpha is equal to pi of 2 plus p, and k belongs to z, y ratio x equals tangent alpha is meaningless. In addition, for an arbitrarily determined angle alpha, the y ratio x value is also uniquely determined. Therefore, when x is not equal to 0, the ratio of ordinate y and abscissa x of point P corresponding to real alpha is the corresponding relationship of tangent function. So does the definition of any trigonometric function meet the definition of high school function? Let's look at sine function, cosine function, and tangent function, which take angle as independent variable and take the coordinates of points on the unit circle or the ratio of coordinates as function value. Since a one-to-one correspondence can be established between the set of angles and the set of real numbers, trigonometric functions can be regarded as functions with real arguments. According to the definition of function and common symbols, we usually record it as sine function y equals sine x, cosine function y equals cosine x, and tangent function y equals tangent x. Then we call sine function, cosine function, and tangent function trigonometric function. To study functions, we should first study the definition domain of functions. So what are the definition domains of trigonometric functions with arbitrary angles? Obviously, the definition domain of sine function is the set of real numbers and x belongs to R, and the definition domain of cosine function is the set of real numbers, that is, x belongs to R. In the process of defining tangent function, we found that the middle of angle alpha cannot be located on the y-axis. At this time, x cannot be equal to half pi plus p, and k belongs to z. Therefore, the definition domain of tangent function is that x is not equal to half pi plus p, and k belongs to z. What is the difference between this definition and the definition of acute angle trigonometric function? The trigonometric function of any angle is defined by the coordinates of the intersection of the angle and the unit circle, while in junior high school, the acute trigonometric function is defined by the ratio of the side length of the right triangle. In the cell, the hypotenuse of the right triangle is 1, so the acute trigonometric function can also be determined by the coordinates of the end edge of the angle and the intersection of the single element. At this time, the points on the final edge are all in the first quadrant, so the trigonometric function values of acute angles are positive, while the trigonometric function values of any angle can be negative. So what is the significance of taking the value of trigonometric function as a negative number? In the previous lecture, we know that the mathematician Euler played an important role in the development of trigonometric functions. His research on trigonometric functions is mainly applied to the changes and laws of the real world, such as physical sine waves. Therefore, the value of trigonometric function can be taken as a negative number, which is not only of mathematical significance, but also of practical significance. So what are the similarities and differences between trigonometric function of arbitrary angle and trigonometric function of acute angle? In fact, we can find that the trigonometric function of an acute angle is a function of the trigonometric function of any angle defined in the 0 to pi of 2 open interval. Let's take a look at this example. The first question is to find the sine, cosine, and tangent of 5/3 of pi. In the previous analysis, we know that to study the sine, cosine, and tangent of an angle, we need to know the coordinates of the intersection of its terminal edge and the unit circle. Therefore, we should first make 5/3 of the pi. Draw the intersection B between the final edge and the unit circle. Make a vertical line through the x-axis in direction B. Study the length of two right-angled sides in a right triangle. We can get that in a right triangle, the coordinates of the intersection of the angle AOB, the terminal edge, and the element are 1/2 and -3/2. Therefore, 5/3 pi of sine is equal to the root of -1/2 sine 3. 5/3 of the cosine pi is equal to 1/2, and 5/3 of the tangent pi is equal to the ratio of the ordinate and abscissa is equal to the negative root sine 3. Then trigonometric functions cannot be evaluated without the unit circle. If the position of point P at this time is not the intersection of the unit circle and the final edge, what should be done? As shown in the figure, let alpha be an arbitrary angle, and any point P on its final edge does not coincide with the origin O. The coordinates of P are x, y. The distance between point P and the origin is r. Prove that sine alpha is equal to y ratio r, cosine alpha is equal to x ratio r, and tangent alpha is equal to y ratio x. Let's first analyze whether you can draw a graph to represent sin alpha and cosine alpha according to the definition of trigonometric function. Second, what do you mean by y to r, x to r, and y to x in your graph? Can you find the relationship between them and the trigonometric function of any alpha? So let's go back to the definition of trigonometric function of arbitrary angle. Make a unit circle. Suppose that the terminal edge of the angle alpha and the unit circle intersect at point PO. We make a vertical line through the x-axis in the direction of P0, and the vertical foot is MO. It can be found that the y ratio r is related to the coordinates of point P in the unit circle, and the ratio of the vertical coordinates to the radius. Because triangle OMP and triangle OMOPO are similar triangles. Because P0 and P are in the same coordinate system, the abscissa and ordinate of point P and point P0 are the same sign. So we can study this problem through it. The final edge of the angle alpha and the unit circle meet at point P0. The coordinates of P0 are x0, y0. We pass through points P and P0 respectively, and make vertical lines PM and P0 meter 0 to the x-axis, with vertical feet M and M0 respectively. So we know that PM is equal to the absolute value of y, and P0 meter 0 is equal to the absolute value of y0. OM is equal to the absolute value of x, and OM0 is equal to the absolute value of xo. In the previous analysis, we found that triangle OMP is similar to triangle OMP0. So we can know from the length relationship that the ratio of POMO to 1 is equal to PM to R. That is to say, the absolute value of y0 is equal to the ratio of y to r. Since y and y0 are positive and negative, yo is equal to y ratio r, that is, sine alpha is equal to y ratio r. Similarly, cosine alpha is equal to x ratio r, tangent alpha is equal to y ratio x. Example 2 actually gives another definition of trigonometric function of arbitrary angle, which is equivalent to the existing definition. Can you describe this definition in strict mathematical language? In general, for any angle alpha, the coordinates of any point P on the terminal edge of the angle alpha are x, y, and the distance from it to the origin O is r equals up equals ohm square under the root sign plus tm square, which is x square under the root sign plus y square. Then sine alpha is equal to y ratio r, cosine alpha is equal to x ratio r, tangent alpha is equal to y ratio x. Obviously, the trigonometric function value of any angle will not change with the position of point P in the middle. According to the definition of trigonometric function at any angle, we know that the sign of the trigonometric function value is different with the position of the end edge. Can you fill the symbols of the three trigonometric function values in each quadrant in the brackets in the figure below? First, let's look at sine alpha. Sine alpha is equal to y ratio r by definition, so its sign is determined by the sign of y. Obviously, sine alpha is positive when the middle is in the second quadrant. When the end edge is in the third and fourth quadrants, sine alpha is negative. Similarly, cosine alpha equals x to r, so its sign is determined by abscissa. Therefore, when the ordinate is in quadrants 1 and 4, the cosine alpha sign is positive. When the final edge is in quadrant 2 and 3, the cosine alpha sign is negative. Tangent alpha is equal to y over x, that is, when y and x have the same sign, tangent alpha is positive. Therefore, tangent is positive when the terminal edge is in the 1 and 3 image limits. Similarly, when the final edge is in quadrants 2 and 4, tangent alpha is negative. From this, we can judge the sign of trigonometric function, because the sign of trigonometric function is related to the position of the quadrant where the middle of the angle is located. Therefore, we only need to explore the quadrant position of the final edge of the three corners. Since 250 degrees is the third quadrant angle, sine 250 degrees is less than 0. Because the negative 672 degrees is equal to 48 degrees minus 360 degrees multiplied by 2, the middle of the negative 672 degrees is the same as the middle of the 48 degrees, so the negative 672 degrees of tangent is greater than 0. Third, because 3 pi is equal to pi plus 2 pi, the terminal edge of the 3 pi angle is located on the non-positive half-axis of the x-axis. So tangent 3 pi is equal to 0. In today's study, we learned how trigonometric functions are defined. In addition to learning the definition of unit circle, what other definition methods do we have? First, let's look at the definition of unit circle. By establishing a rectangular coordinate system, we make the vertex of the angle alpha coincide with the coordinate origin, and the endpoint and the focus of the unit are P. The definition of the trigonometric function is obtained from the coordinates x and y of the point P. Y equals sine x, x belongs to r, which is a sine function. Y equals cosine x, x belongs to r, which is the cosine function. Y is equal to tangent x, x is not equal to bisection pi plus k pi, k belongs to z, which is a tangent function. We also study the terminal edge definition method. After establishing the rectangular coordinate system for any angle alpha, the coordinates of any point P on the terminal edge of the angle alpha are x, y, and the distance from it to the origin O is r equal to the square of x under the root sign plus the square of y. Then sine alpha equals y to r, cosine alpha equals x to r, and tangent alpha equals y to x. That's all for this lesson. Goodbye.